Dear friends, welcome back to this series on physics of solids. In the last session, we started a discussion on the models which on the models which can be applied to understand the electronic conduction in a metal. There we already talked about the classical modeling of the classical free electron model, which was proposed by Drude and Lorentz to understand the metallic conduction. But as we told in the last session itself, there were, although the model was a success in order to understand many basic phenomena associated with the electronic conduction, there were definitely certain shortcomings in the model. So, in order to improve on the model, there were models which needs to be proposed based on the quantum mechanical concepts. So, before getting into that picture, let me ask you, why is a crystal or a metal, for example, is transparent to conduction electrons? For a student in science, he will necessarily identify two things which are important to the transparency of conduction electrons to a metal. One could be the periodicity in a crystal, right? The periodicity which we talked already in the already in our previous sessions. And second could be the one which is proposed by the Pauli's exclusion principle, because the Pauli's exclusion principle will tell you that no two electrons cannot be found at the same position at the same instant, because that will so therefore, when there has to be a distance between the two particles. So, whenever a particle comes near a particle, the Pauli's exclusion prevents them to be together at the same point at the same instant. Therefore, the particle has to be really continuously conducting or allowing the particle to continue. So, that is a more lower energy situation. So, those two situations can be spotted as or two fundamental reasons why the conduction electrons are transparent in a metal or a crystal. So, our model, the new model which we need to discover based on quantum mechanical perceptions also, has to definitely take into account these matters also. So, as we discussed towards the end of the last session, we told that there was this Fermi-Dirac statistics which was coming up in the field of science in the last century, and then people started exploring the possibility of applying the Fermi-Dirac statistics into the free electron model. So, it was first applied by Sommerfeld. So, in the theory of Lorentz, it was assumed that the electrons obey classical rules and the Maxwell-Boltzmann statistics. Now, Sommerfeld introduced the concept of quantum mechanics into the free electron theory, and therefore, the Sommerfeld model is sometimes known as the quantum mechanical treatment of free electron gas. In 1925, Pauli discovered the exclusion principle that no two electrons may be found in the same position at the same instant of time. But then in 1926, Fermi and Dirac separately derived what we now call as the Fermi-Dirac statistics, right, and that was based really on the quantum mechanical foundations. So, upon learning of this Fermi's proposal or the Fermi statistics, Sommerfeld realized that this Drude's theory of metals could easily be generalized to incorporate Fermi statistics, and therefore, he incorporated Fermi-Dirac statistics into the concept of free electron gas. And to tell you this Sommerfeld model is noted for two main points. One, it recognizes that their energies are discrete and treats them like a particle in a box of constant energy, right. The electrons or the particles which transmit transfer electrical conduction or carry out the electrical conduction is considered to be that their energies are discrete and treats them like particles in a box of constant energy. It uses Pauli's principle to distribute them in available energy states. In order to get into let us see further into the Sommerfeld model. So, here first let us consider an electron confined in a say in a one dimensional box of length L with potential anywhere in the box as constant as 0 and a very high potential at the boundary approaching infinity. It is a very typical one dimensional box problem which you study in a quantum mechanics class, right. So, what is the Schrodinger equation in that case? So, H psi is equal to minus of h squared by h cut squared by 2m into d squared psi by dx squared, right, assuming that your v is equal to 0, right, and that is equal to E n psi n, where E n is the eigenvalue of the system, or it is the measure of the energy of the system. So, now we can assume a general solution to this expression psi n is equal to a sin n pi x by L, right, for that expression, and on substitution one can find a value of the constant a to be equal to root of 2 by L, which is very straightforward assumption, where you know that psi star you calculate, then you will reach the probability, and from there you will reach the you will find out the value of a, which is which you will find in a very introductory book, even in an introductory book of quantum mechanics, right. I am not trying to do that here. So, root of 2 by L, and the energy eigenvalue would be equal to E n is equal to what, h cut squared by 2m into n pi by L the whole square. So, there are different ways of expressing that. Different books will put it in different formulation. In any case, is only one. Sometimes people may put h cut is equal to h by 2 pi, and therefore you can always modify the equation. So, E n is equal to h cut squared by 2m into n pi by L the whole square, and the Fermi energy which is corresponding to be equal to h cut squared by 2m into n f pi by L the whole square. So, I forgot to tell you from where does this Fermi energy comes up. So, Fermi energy means it is that energy which an electron can have, the highest energy which an electron can have at absolute 0 of temperature, right. So, that is a limiting situation, and if I assume that if there are total n number of electrons, capital N number of electrons, the NF will be equal to n by 2, because in every situation, in every orbital you have 2 electrons, right, one which is of the up spin and another of the down spin. So, therefore, if I have total n number of electrons, the NF which we talked about will be equal to n by 2, and therefore, the expression of the epsilon f or the EF of the Fermi energy can be modified as h cut squared by 2m into n capital n pi by 2L raised to 2 or squared. Now, if we extend this formulation into a 3-dimensional system, it is quite obvious that we start with the Schrodinger equation in 3-dimensional, which we will write it as minus of h cut squared by 2m into, we have 3 directions, dou squared by dou x squared plus dou squared by dou y squared plus dou squared by dou z squared into psi k r, right, where r represents x, y and z directions, which is equal to E k psi k r. and if you are assuming a cube of side L, the wave function will be, again you will start assuming a standing wave solution for that, because we are assuming a situation in a 3-dimensional box, and we have our solution also has to be in correspondence with that, and then the solution will come to be psi n of r is equal to a sin n pi x by L into sin of n y y pi by L into sin of n z z pi by L. Now, this wave equation must obey the condition of periodicity. We already talked in the beginning of that, right. So, I can always write psi of x plus L y z is equal to psi of x y z, right. So, now, since the wave equation is obeying the Schrodinger equation and the standing wave solution, I can extend this to write to get into a travelling, I can model this situation into a travelling plane wave, which I normally write, which one will normally write it as psi k of r is equal to exponential I k dot r. So, what will be the value of k x, k y and k z? You will know the answer for that, equal to k x, k y, k z can be 0 or plus 2 pi by L plus or minus 4 pi by L, where L is the length of the one side of the box which we imagined. Actually, this travelling plane wave solution is actually representing an orbiter, one single orbiter, right. So, both those equations, equation number 3 and 4 together should satisfy this periodic condition E exponential I k x into x plus L equal to exponential I k x, k x x. So, substituting that equation 4 into the equation number 1, you will get E k equal to h cut squared k squared by 2 m equal to h cut squared by 2 m into k x squared plus k y squared plus k z squared. So, what does it suggest? Now, you are having an equation which is a square based equation k x squared plus k y squared plus k z squared, x, y, z direction. So, what will be the kind of image you will visualize? You will visualize a sphere, right, because it is a pure mathematics. So, you will visualize a sphere which, since we started imagining based on a Fermi sphere, on a Fermi energy, we call it as the Fermi sphere, a Fermi sphere of boundary E f, because that is what we discussed about the E f for the Fermi energy. It is the biggest, is the highest energy which a electron can process. So, E f can be written to be, can be expressed as h cut squared by 2 m into k f squared. Now, the volume of the electron state in 3 dimension is based on the box formulation which we got, it can be equal to be 2 pi by L the whole cube, right, 2 pi by L whole cube. What is the sphere, volume of the sphere? So, then the question you could ask me is that what is the radius of the the Fermi sphere? What is the radius? It is given by your wave vector, which is k f. So, the volume would be 4 by 3 pi k f cube, and the next question which one could ask is that, okay, now you have the volume of one electron state and you have the volume of the Fermi sphere. Okay, now tell me what will be the total number of orbitals? Answer is very simple, right, because you have to basically divide the sphere of the volume of the sphere, the Fermi sphere, with the volume of one electron state. I just do that. But one thing to be noted, to be remembered is that we have to always multiply it by 2 if we need really the number of electrons. So, if we take the number of electrons to be capital N, I will write it as 2 into 4 by 3 pi k f cube divided by 2 pi by L the whole cube. And if I take the L cube to be equal to capital V, I will get it to be V by 3 pi squared into kf cube, which is equal to n, or the kf gives the measure of the Fermi sphere. So, kf is equal to 3 pi squared n by V raised to 1 by 3. And correspondingly you can always calculate the value of the Fermi energy, right. So, Fermi energy then can be evaluated as h cut squared by 2m into 3 pi squared n by V raised to 2 by 3, and from that expression you will again calculate, you will be getting the value of n in terms of the energy. So, what will be that? You can always very simply work out with a pen and paper to be equal to V by 3 pi squared into 2m by h cut squared raised to 3 by 2 e raised to 3 by 2, which means that n is directly proportional to e raised to 3 by 2. That is a very important information, right. Now, what will be the density of states, right? What is the density of states means by the way? The density of states means that the number of orbitals per unit energy range. So, in any case, in any situation in science, the density of states means that what will be the number of states in a particular range of energy or a particular range of frequency or a particular k range, right. Here we are talking about an energy range. So, now we have the evaluation of the number of electrons capital N, and from there you can calculate the density of states to be equal to dN by dE, which will be evaluated as V by 2 pi squared into 2m by h cut squared raised to 3 by 2 into e raised to half. Now, if I plot that expression between the density of states in the y axis and energy in the x axis, you will get a plot similar to the image you see there, right. And of course, you will we are always assuming a Fermi Dirac statistics, and those who know the Fermi Dirac statistics know the significance of the slope which is there near the Fermi energy. I am not getting seriously into that portion. Now, further the ln of n, which is we have already calculated the n, right, and which will be the number of electrons, and that is equal to 3 by 2 ln E plus constant, and which will come to be ln of n can be expressed in terms of dN by n equal to 3 by 2 dE by E, and therefore, the density of states of particular energy E dE by dE is equal to 3n by 2E. So, what does that means by the number of orbitals per unit range at Fermi energy is the total number of conduction electrons divided by the Fermi energy. Now, the next task would be to connect this quantum mechanical free electron model with the electrical conductivity and the rule which we know from the beginning, which is the Ohm's law. Let us try to do that. Let us try to see if this quantum mechanical model is really approving of the Ohm's law. So, how to do that? Now, we observe the electron from a force equation F equal to m into dV by dt. So, V equal to h cut k, right. So, F is equal to h cut into dk by dt is equal to minus of E into E plus 1 by C into V cross B. Now, if we imagine that there is no external magnetic field which is applied, the integration of that equation would give you kT minus K0 is equal to minus of EET by h cut, or delta K equal to minus of EET by h cut. Delta K equal to minus of EET by h cut. So, what does that mean by? Now, you are actually projecting a situation where you have a Fermi sphere, right, which is of a particular radius, which comes from the wave vector value. Now, you are telling that when you apply an electric field, you are observing a motion in the Fermi sphere, delta K equal to minus of EET by h cut. Now, as you can see the image in the image, you have you have a Fermi, you have a reciprocal space, and the blue dot there is actually showing the filled spots, filled states, and there are possible k values which is being filled by the electrons. But here in this situation delta K is equal to 0 and the net momentum is equal to 0. Now, what is the situation you need? You need to apply an electric field. So, I apply an electric field, then the picture will get modified like the one which I have shown in the image there. The Fermi sphere will slightly move forward. So, if there are n electrons, the total momentum will be n into h cut delta K, and the energy would differ simultaneously. So, you applied an electric field and your Fermi sphere started moving. Is that picture quite stable? Or another way of asking the question is that, can the Fermi sphere go on moving or shifting forever? Because nowhere in that expression of delta K you suggested any kind of hindrance for the motion of the electrons. It is just simply a function of the electric field. So, what is that? So, what is can the Fermi sphere go on moving forever? The answer is no. In any case, one is very if the Fermi sphere would have been moving forever, the current would have been conducted each and everywhere, and the world itself would have been totally different. We do know that there is something called a resistivity, right, and again, even in our assumption, we imagine that there is a huge boundary in which the electron can move through. Here in the reality, because of the collisions of the electrons with impurities, lattice imperfections and the phonons, the displaced sphere may be maintained at a steady state in an electric field. So, that is the real case. So, if the collision time is represented by tau, the displacement in the Fermi sphere is given by given to be, if we invoke the equation minus of E E t by h cut, if we substitute the t by tau, the time between two collisions, right, the collision time. So, t equal to tau, if I substitute, that will come to be minus of E E tau by h cut, or if one can always express that in terms of the momentum also. In that case, the current density which we needed to calculate, we have done this in the earlier case of classical modeling also. The current density will be equal to NeV, right, n is the particle density, right. So, n into charge NeV, which will come to be equal to n e squared tau E by m, but we know that current density is equal to sigma into E. Sigma is the conductivity. We already calculated that n e squared tau by m is equal to sigma, and therefore, J equal to sigma E. So, what is J equal to sigma E suggesting? J equal to sigma E is exactly what we know from the Ohm's law. V equal to IR, or I is equal to V by R, or that if we take the inverse of that, the sigma, right. So, sigma equal to N squared tau by m, or J equal to sigma E, and therefore, this quantum mechanical formulation exactly follows the Ohm's law. And if we calculate the corresponding mean free path of conduction electrons, L is equal to Vf into tau, or the velocity, Vf is the velocity of the Fermi sphere. Now, one of the questions which could come into your mind could be, is it temperature dependent? Yes, it is temperature dependent. If we calculate really, or if we measure the value of the mean free path at room temperature, for example, say for copper, it will come to be something like of the order of 10 raised to minus 6, 3 into 10 raised to minus 6 centimeter, if I remember correct. And at 4 Kelvin, which is really a low temperature, from 300 Kelvin to 4 Kelvin, it really increases to 0.3 centimeter. See the improvement in the mean free path. From 3 into 10 raised to minus 6, it went to 0.3 centimeter at a difference of around 300 Kelvin in temperature. Now, if we see the experimental electrical resistivity of metals, there are again two components, right. There is a lattice component and then there is an intrinsic component. The electrical resistivity of most metals at room temperature will be dominated by collisions of the conduction electrons with phonons, but at low temperature it will be dominated by collisions with lattice imperfections, and therefore, when we write this expression for the collision time, we can write it as 1 by tau equal to 1 by tau L plus 1 by tau I, and correspondingly you can write the expression for the resistivity to be equal to rho L plus rho I. So, but these two components behaves in a different manner, right. So, one is a lattice component, another is led by the imperfections, right. So, if we calculate them together, you will see that rho L is temperature dependent, but independent of the defects, whereas rho I, which is is totally temperature dependent. So, the experimental thus leads to a simple general law. If I plot the corresponding resistance of potassium, you can definitely see that difference over there. If different independent microprocessors are underlying a phenomenon, there is this rule called the Matheson's law. The Matheson's law suggests that if different independent microprocessors underlie the collision of electrons at the Fermi level, the probabilities of collisions are additive. The additivity of the collision rates is actually being proposed by the so called Matheson's law. As you can see in the image there, I have put 4 different types of copper, the difference being the kind of doping difference in the percentage doping with nickel. So, as you can see, the resistivity is totally dependent on the percentage impurity, and the background is actually giving you the fundamental resistance of the material. So, but One of the central characteristic of the free electron model, which is that the electrons are not at all dependent on each other, or they are totally not at all interacting, needed a modification, because that cannot be logically agreed upon, because the electrons do tend to integrate. And newer models came up modifying the free electron models, so that this kind of interactions also could be taken into consideration. So, the Bloch theorem is central to those kind of concepts, and the nearly free electron model also was an extension for that. Those portions will be covered in the next session. Thanks for your attention in this session. See you next time.